This is the first screencast for Chapter 8, Chemical Bonding. So within this chapter, we will take a look at the type of bondings you probably learned last year. Ionic bonding, covalent bonding, and just a little smidgen of metallic bonding. So it's going to be probably a few of these screencasts we'll have for Chapter 8. So some of the stuff you guys remember from last year, some of these definitions, ionic versus these covalent bonding, metallic bondings. We have a pretty good understanding as far as what those mean. We're just going to dig a little deeper into some slight differences between them. So looking at some Lewis structures or symbols on these, you guys do these as well. Whatever group I'm in, for example, group 1 elements all have a charge of 1. So when we're doing a Lewis symbol, we typically will kind of surround that element with that 1 electron if it's in group 1. And if going all the way up to group 8, if it has 8 electrons, we'll surround it with 8. Easy enough. Okay, ionic bonding. Uh, Last chapter, we were looking at some of the energies that were involved in breaking bonds or how some of these bonds kind of come together. And it doesn't make sense. So we looked at the ionization energy. And we can see the ionization energy is the energy that it takes to remove an electron from sodium. So sodium energetically doesn't voluntarily release an electron. It requires that much energy, 496 kilojoules per mole, to remove an electron from sodium. So that's not energetically favorable. And then if you look at chlorine, when it accepts an electron, we have this energy of 349 kilojoules per mole being released. So that doesn't add up. So it still requires about 150 kilojoules for that process to work. So it's not favorable. So there's something else that's missing in the process, because we do know that this reaction is fairly exothermic because salt's fairly stable. We don't have to worry about it breaking apart. So this last thing here is called a lattice energy, which I think we'll introduce here in a slide or so. It's this part where after, basically, we have the sodium in which it's donating the electron to the chlorine atom. But then as a result, this is the part, we have a positive sodium and we have a negative chloride. Once we have that, there's a new attraction between these. And that's the lattice energy. So we saw this equation down here at the bottom in which we have this constant. We won't worry about that. But these are the charges placed upon each of the atoms within the mix, and then the distance between the interchanged atoms, the atoms that are going to eventually attract to each other. So there's some math that can go into here, and I don't know if we put any of that in here or not. No, it doesn't look like it. But yeah, it is coming up here in a little bit. But what we will notice is regards to what affects the lattice energy is more so the charge than the size of the atoms. So we can see as we're moving down the ladder here, fluorine is the smallest, and then chlorine, and then iodine. We notice how the value goes down because the distance is increasing in those atoms. And we do the same thing with sodium. Notice how the value goes down because the distance increases. Going back to our equation over here, we should see that the potential energy between them is going to decrease because this value in the denominator is getting larger. But just to have a simple comparison between, let's say, sodium chloride and magnesium chloride, notice when the charge goes from a -1 to a -2 for chloride, the value almost triples. So it's not a correlation, but we do see a trend that as the charge increases, the size of the lattice energy is going to increase much, much faster than as the distance between them decreases. So which one's more important? Going back to our equation over here, Q is a greater factor in looking at the potential energy difference than distance is. So as the charges increase, the potential energy is going to increase much faster or much larger than the distance has an effect. Okay, oops. So this is a step-by-step process, which we will do in class. looking at the energy values. So it's not as simple as just saying, okay, there's an electron changed and that's it. No. So one of the first things we would have to do is take sodium and turn it into from a solid to a gas. That would be step one, if you'd like. And then you have to, for step two, you have to break apart the bond which is connecting to chlorine atoms. That would be step two. And then you have to ionize the sodium, going from sodium to sodium plus. And then you would take chlorine and have it attract the electron, accept the electron, would be step four. And then finally, once you have the ions, you have the last step in which those two connect, which is the lattice energy, which is the responsible force for that large exothermic process. And all of that is summed up in whatever value this happens to be. All right, covalent bonding, which is we typically think of it as just sharing electrons. So for covalent bonding, you're just simply having attraction between the positive nuclei and the negative electrons. And we have some different comparisons based upon that. So using this example, we just have some computer models that kind of show the differences. If you have two atoms which are the same, in this case fluorine being connected to fluorine, they're exactly the same atom, so they share electrons equally. But in this model over here, having hydrogen and fluorine, fluorine is much more electronegative, which we'll introduce here in a second. It attracts electrons much more strongly, so the electron pull is going to be towards fluorine and away from hydrogen. So here is that table. Electronegativity is the ability to attract electrons, and it's a combination of ionization energy and electron affinity, and it's actually even a little bit more, but that's what we're really going to base it on. And we can see as a general rule that electronegativity is going to increase from left to right and from bottom to top of the table. So those are the trends we'll be looking at. These values have no units, as it states right here. So they're just comparative values that a guy named Linus, I believe, is the one who introduced these. And there's several different ways we can look at this electronic difference between atoms, but this is the one we primarily use. We'll see another one here in just a little bit. But fluorine is given the arbitrary value of 4, and everything else is relative to that. So just notice these top right-hand values or elements. Nitrogen with chlorine, they have both a value of 3.0. But remember, when we get to hydrogen bonding, we really are focusing on just the top 3. And it has mostly to do with the size of the atom. Okay. So with polar covalent bonds, this next way we can kind of look at it is with this little dipole moment, and it's kind of the same idea in looking at the electronegativities, but it looks at the charge a little bit differently. So when we look at it as an example, when we look at sodium chloride, we like to say that sodium is a +1 and chloride is a -1. When we go through this process, and it's a little too lengthy in the math to go through in the presentation here, but when we look at it mathematically and go through this process of Q, which is the relative charge, and that's a constant value that we'll look at here. And then the distance between the atoms, we can go through and determine what the dipole moment actually is. And it's measured in a unit called divides. And again, when we're in class, we'll do a better job of actually looking at this. Afterwards, once we have a value, we can experimentally go backwards and determine what the actual charge difference between some of these atoms would be. So looking at these, again, it's another way to kind of look at the electronegativity differences. So we have these values, and notice that if we look at that previous formula we had there, in which we had Q and R, the idea is that we have this dipole moment. This is supposed to be like a mu, not an n. We look at the differences between these. Notice that the electronegativity is going to decrease going down because, again, fluorine is very electronegative, and it's going to decrease down the group. That's the only difference. The bond length is actually going up. So if we were to use this as a comparison to the dipole moment, the radius is going up but the relative charge is going down. Yet the dipole is increasing, or excuse me, decreasing, is decreasing. So what we'll see is what is much more relevant is the Q value. That Q value, which is the charge differential between these two, is more influential as in a decreasing value for the dipole moment. And again, this will be much more clear when hopefully when we do the conversation in class. All right, this is a good place to stop for the end of lecture number 1.